Wow, looks like it's about 8:15, so we'll go ahead and we'll get started. If people come in and out, that's okay. Hello, everyone. My name's Andy Rivenes. I'm a product manager with Oracle for database and memory. So today we're going to talk a little bit about how database and memory works, and I'm going to show you some examples, which is always a little bit more fun because it makes it a little easier to kind of visualize how database and memory actually works. My email address is there if you have any questions that I'm not able to cover or answer for you today. You can always email me if you think of something later. It looks like you can type into the chat. There's a chat box for the room chat. So I will do my best to try to answer questions. If I get distracted, then I may defer to the end, but I'll try to, if it goes with the flow, I'll try to answer your questions as we go if you have them. You can follow me on Twitter. And then we have our blog, which I'll probably mention throughout the session. I will have some links at the end that you can use. I assume we'll upload presentations and you can access those. But our blog, it's the Oracle Database and Memory blog. Both technical articles and then other articles about database and memory. And then I have a nice resources page I usually refer to, kind of what I think of as our portal into database and memory. So our Ask Tom office hour sessions, our video channel, any technical papers that we've got. It's kind of a nice index into information about database and memory. So with that, we will go ahead and get started. Our safe harbor statement, I may mention some futures, so that's just kind of Oracle's way of handling that. So why use database and memory? So people kind of hear in memory and they assume that everything's going to be faster. And so that's kind of I like to start off with some of the use cases for database and memory, and then we kind of launch into how it works and what all the features of database and memory are. So traditional reporting. So clearly, so database and memory isn't going to speed up OLTP or insert updates and deletes DML type activity. It's really focused. We'll talk a little bit about this. Actually, we'll talk a lot about this. Columnar formatted data, it is in memory, so it's targeted at reporting. So traditional reporting, I usually tell folks that if we don't get at least a 10x improvement in reporting, and you think about it, 10x is huge, then I'm disappointed. And so kind of the nice thing about database and memory, since it's fully integrated in the Oracle database, you don't have to change any of your existing applications. So whether it's a homegrown application or whether it's a third-party application, you can just enable database and memory, populate objects, which we'll talk a little bit about, and don't have to do anything else to take advantage of it. And then it will speed up your analytic reporting. The secret sauce behind all that is the cost-based optimizer. Again, I'll talk a little bit more about that. But the first thing to think about is traditional reporting. Anytime where you're running analytic reports, looking through a lot of data, database and memory is going to help. In addition to that, something that there's a lot of talk about, but people don't really, I don't think, do a very good job of focusing on, is something we call real-time analytics. Since database and memory is in memory and CPU, since we can operate on anything in the Oracle database, very often you can actually run a lot of your analytic reporting, maybe BI dashboards, right on the source data and make decisions in real time. And there's a lot of, if you go Google real time, there's a lot of complicated Apache and open source type software where they talk about streaming data, and all of that's relevant for real-time analytics. But what we mean by real-time analytics is being able to actually mine your existing data in your Oracle database, and actually external as well, since we support external tables, population directly into Oracle database. Being able to actually answer questions directly on your data without having to wait for it to be either transformed, moved to maybe a data warehouse, certainly works in those environments well. But I think the real game changer is the ability to operate directly on your data in real time. And that's what we mean by, what I mean by real-time analytics. In addition to that, since database and memory is accessing this data in columnar formats, we don't need analytic reporting indexes. So typically, folks have had to add a significant number of analytic reporting indexes to both their OLTP or mixed workload environments and possibly even data warehouses to get their reports to run efficiently, quickly. Database and memory doesn't access indexes, at least not traditional B-tree type indexes or bitmap-based indexes. And so being able to eliminate those analytic reporting type indexes that have had to been added can save a significant amount of DML work or resources because you have to maintain those indexes, not to mention the disk space required, plus the undo and redo generation, and backups for that matter. So we've got several customers, Walgreens one, Bosch is another. All of these stories are available on oracle.com. In our database and memory page, we've got a lot of customer stories where customers talk about how they've been able to use database and memory. So that's not something or is a significant part of database and memory is the ability to reduce the need for indexes and that index overhead. Now, I'm not talking about primary key, foreign key type indexes, constraints, lookup indexes. Typically, since it's a cost-based decision to use database and memory or in-memory format versus the traditional row format, it may be that certain indexes are still required for very quick lookups of just a few rows. We'll kind of actually cover that in some of the examples, but I'm not saying drop all your indexes, but your analytic reporting indexes. Hopefully I got that clear. So what is database and memory? So database and memory is fully integrated in Oracle database. It's an option, so you do have to pay for it. We have kind of an exciting new offering, and we first released it in the 20C or the 20.3 pre-release. We've backported it, and I'll talk a little bit about the base level feature, so you can actually use parts of database and memory without having to pay for it in your production, your normal environments. But database and memory is an option. To fully use it, you have to pay for it. Targets real-time analytics, accelerates mixed workload by being able to not only access data just with CPU and memory, not having to do I/O, but also the fact that by being able to reduce or drop a lot of your analytic reporting indexes will free up capacity and make it available. Other aspects of your Oracle database, your OLTP workload, can usually be significantly sped up by not having to maintain all those indexes. Proven scale out, risk-free. It's basically, think of it as just part of Oracle database. You don't install anything separate. It's just installing Oracle database starting in 12.102 and above. It's just part of Oracle database. You don't have to change any applications because the cost-based optimizer decides, do I access the data in memory in the column store, which I'll talk about in a second, or in the row store. So it's all fully integrated, and all the other applications or technologies that you may be using with Oracle database still work. We don't prevent you from using any of the underlying database technologies like RAC or DataGuard or your backups. And we also don't prevent you from using any of the applications because, again, it's a cost-based decision, and so it's just Oracle database. Hopefully I got that clear as well. But I did want to talk a little bit about this. So kind of the real crux of database and memory is that we support both a columnar format and a row-based format. Row-based formats are great for OLTP. We have the data in a row, so all of the column attributes are together in a row in memory, very easy to manipulate. Oracle database is a very fast transaction processing database. Columnar formats are actually better at analytics, being able to scan lots of data. You only have to scan the columns involved in the query. They vectorize well, they compress well, and so it's very good for analytic reporting, but they really aren't very good for OLTP. You have to, since it's in columnar format, in order to do OLTP, to get it into a row format, you've got to essentially stitch together the column attributes that match with a given row, and there's overhead in doing that. So columnar-oriented databases haven't been very good for OLTP. With database in memory, we actually give you the best of both worlds. You can actually, we haven't changed Oracle database, so your data always exists in the row store, always exists on disk. All of the Oracle transaction architecture hasn't changed. But in addition to that, you can specify tables to be populated in memory in the columnar format. And then it's a cost decision. Does the database access that data based on your query in the row format or in the columnar format? And with that, we basically keep the row format and the columnar format simultaneously and transactionally consistent. Again, Oracle hasn't changed the transaction architecture of Oracle database. You always get a read consistent view of the data. We keep the column store in sync with the row store, very similar to what we do with indexes. However, since the column stores are pure in memory format, we don't have any redo or logging associated with it. You don't change data in the column store, you change data always in the row store. So your inserts, updates, and deletes are always transactions in the row store. All of the redo and undo generation, the backup, it's always safe and never changed. So it's fully ACID compliant. And then the data is also reflected in the column store in metadata, and then in the background we'll asynchronously repopulate that data, but you'll always get a read consistent view of your data, whether the optimizer chooses to access that data in the row format or in the columnar format. And it's simple to implement. All you actually have to do is set an in-memory underscore size initialization parameter to the size you want of the column store to be. I'll go into a little more detail about that. Alter tables, partitions, subpartitions, or materialized views to be in-memory enabled, and then we'll asynchronously populate those objects in the background, and then possibly drop your analytic reporting indexes. That's literally it. Oracle database does the rest of the work for you. There is some devil in the details, and I'll kind of go into that a little bit, but realistically, that's it. You allocate the column store in the SGA, enable objects to be populated in the column store. We'll asynchronously populate those in the background, pure in memory format. If the database were to go down, we would repopulate when the instance comes back up, since it is pure in memory, and then dropping analytic reporting indexes. And that's really as simple as it gets. And that's all it takes to do or to take advantage of database in memory. Where is it available? So database in memory, again, as I mentioned, it's an option. It's also available in the cloud. And essentially cloud, the extreme performance versions of the cloud, any of the Exadata cloud services, Exadata Cloud at Customer, Autonomous Data Warehouse uses database in memory on the flash storage. So the flash version of it, I'll talk a little bit about the cell memory option, or the ability to use not only DRAM or memory in the SGA for the column store, but also if you have Exadata, being able to use your flash cache, which is typically terabytes, is a secondary columnar data store, if you will. So I can give you the ability to have terabytes of columnar formatted data for your analytics. Obviously on premises, that's where we started with 12.102, the first patch set. Continued to update. Oracle database in memory is an actively developed product, so we continue to make changes. 12.2, 18C, 19C, the 20.3 pre-release, we actually added a bunch of features which will then come out in the next full-blown release of Oracle Database, and actually even Oracle Database XE. So you can run database in memory as part of Oracle Database XE if you want. If you're using Database XE, you get up to 2 GB of memory with XE, and you can use, I think I've gotten it to about 1.5, maybe a little bit more memory allocated to the column store, because obviously you still need some memory for the other parts of the SGA for Oracle Database. But basically anywhere Oracle Database runs, database in memory can run. Which version should you upgrade to? I include this mainly because I typically talk to folks that are not only interested in database in memory, but also want to implement it. And 19C is really the Oracle's targeted long-term release. I think I have this slide, the latest version. It does seem to change. So I apologize if it's the dates are slightly off, but I don't think so. I think I've got the latest version. But the key is that 12.102 has been out for a long time. It's really in extended support. 11.2, if you're there, you're probably thinking of upgrading. And if you're going to do an upgrade, 19C is really where you ought to land. Notice it says below the Oracle 19, 12.203. So we're really in the last version of the 12C release line. And so 19C really should be your target. And database in memory, again, has been fully, we continue to develop and add options and features to it. So 19C really should be your target and what you should be thinking about. And with that, let's talk a little bit about how database in memory works. So I mentioned it's a pure in-memory format. It's columnar, so we can scan that data very, very fast. We only have to access the columns we're interested in. I mentioned tables, partitions, subpartitions, and materialized views all can be populated in the column store. Since it is columnar formatted, it tends to compress fairly well. We have several different flavors of compression. The default typically gets at least a 2x compression rate, sometimes more. And it's available on, as I said, on all, basically anywhere Oracle database runs, 12.102 or above, database in memory will run. So let's talk a little bit about some of the more technical aspects of database in memory. So what we're doing is, I mentioned the in-memory underscore size parameter. We're going to allocate based on that parameter, the size that you provide to that parameter. We're going to allocate an area, an in-memory area, if you will, in the SGA. And so you have to have enough memory in your database server to support that. I tend to tell people, don't steal memory. In other words, if you have a running system and you have the buffer cache and the shared pool and the other pools that are in the SGA sized already, if you steal memory from those areas, typically your existing workload could very well suffer because the DML, the existing workload, the SQL statements that get parsed and cached in the library cache will not have as much room as they would have if you take memory from it. So always think of adding additional memory. This is the in-memory part. Always think of adding additional memory to support the column store. And I'll talk a little bit about how you figure out or how you might decide how much memory that would be. We do have some tools for that. But the bottom line is, from an architectural standpoint, it's just another area in the SGA. Now, the other thing that to take into account, though, is it's not a cache. So the in-memory area is a store. So when you populate a table, partition, whatever, into the column store, when you enable it and Oracle Database populates that data, it stays in its entirety. So unlike the buffer cache, which will typically only have a small number of database blocks, if you will, cached in the buffer cache for each object, we're going to populate the entire object. And so, because as we scan, we want that data to be in memory. And so we're not going to automatically flush out parts of an object to make room for more objects. And so it is possible to fill the in-memory area to the point where no more data can go into the in-memory area. And so that's just another thing to keep in mind, that there is a sizing aspect or a capacity aspect to the in-memory area. It is possible, starting in 12.2, to dynamically resize or increase the size of the in-memory area. To decrease it or to allocate initially, you have to start the instance up. But that still implies that you have enough room in the SGA to accommodate that. So hopefully that's clear. The in-memory area is actually comprised of two pools. A 1 meg pool, which is this IMCU pool. It's on the left of your screen here. And then a 64K pool, which is these SMU or metadata units that are on the right side of your screen. I'll go into a little more detail and show you how you might figure that out, but it's not really all that important other than to recognize the underlying architecture of database and memory and how it works or interacts with Oracle database itself. Oh, I should mention IMCUs, in-memory compression units. So, and actually, let me just skip to this slide. When you populate an object, it will be populated the columnar formatted data. So we'll read the row data, we'll transform it into columnar data, and it will be comprised of one or more of these in-memory compression units. And each of those in-memory compression units will be made up of one or more of these 1 meg areas or memory areas in the in-memory area in that 1 meg pool. So think of it as, say, extents on disk, but it's extents in memory. And so as you populate an object, it'll be made up of one or more IMCUs that are taken from the 1 meg pool. And then each of those IMCUs will have an SMU or a snapshot metadata unit, metadata associated about that columnar data, any changes that occur between the time the IMCU is first populated and possibly repopulated. Talk a little bit about thresholds. As data is changed, we won't immediately change it in the IMCU. The IMCU is read-only, and we'll, based on a threshold, we'll repopulate that data. And those SMUs, or that metadata, will be taken from the 64K pool. Now, you can't change I don't know if you can see my mouse. So you can't change the allocations of the 1 meg and 64K pool. That's fixed based on the in-memory _size parameter. Actually, I'm going to skip to this slide. I always forget I have these two slides. And let me, so the in-memory area, there's, of course, a $V view. So $V in-memory area. Notice here, you see an example with the 1 meg pool and the 64K pool. So this gives you an idea of the overall space allocated and used for the in-memory column store, the in-memory area. And then we have we actually have quite a few $V views because it wouldn't be Oracle database, so we didn't have $V views. But the other key one is the $V IM segments view, and then that gives you an idea of which objects are populated and how much memory they're allocating. Now, I've only included a couple of attributes here. There are a whole boatload of attributes associated actually with the $V IM segments view. But the key is that you can determine what objects are populated then, how much memory they've taken, and whether they're fully populated. So you might think, well, what happens if I run out of space and I can't, say, either fully populate an object or it doesn't go in or get populated at all? So if it's partially populated because you ran out of space, then when a query runs, we'll access that data in the column store, as much of the data that's populated, and any other data we'll access from the row store. So you'll always, your application will run, your SQL statements will still run, you won't get an error, but it won't be as fast as if all of the data was populated. And then if objects are enabled for in-memory but not populated, then we'll just access that data as we would from the row store as if it wasn't populated at all, which actually it isn't. So let me go back real quick. Whoops. To this slide. So I want to talk a little bit about population. So you've allocated your column store, you've brought the database up, you've altered tables in your application. I mean, maybe your entire schema, you just alter all of the objects in your schema to be populated in the column store, or maybe you've chosen certain objects. I should mention that one of the reasons we called it database in memory and not in-memory database is because you get to pick and choose the objects that you populate. You don't have to put the entire database in the column store. And that's a great flexibility. It's much different than, say, ×10, which is an Oracle in-memory product, or some of our competitors that require you to put the entire database in memory. You actually get to pick and choose the objects that you want to populate. And I'll talk a little bit about why you might do that. But as you alter a table to be in memory, it's literally alter table sales in memory, you can choose priorities. So priority just says, based on a priority level, we'll populate those objects first, and objects with a lower priority level will populate after we get the highest priority level objects populated. After that, everybody's equal. All the objects are equal in the column store once they're populated. The optimizer is just choosing based on cost. Doesn't make sense to access that data from the row store or the column store. The default, by the way, is priority of none, and that says we won't populate that data until we first access it. Generally, I recommend setting a priority so that that data will be populated either once it's enabled or when you restart the instance, so that it'll be back in the data and in the column store, so your applications can take advantage of it. Population occurs asynchronously in the background. That's what these Aura W processes are, and I have a little format here. By default, CPU count divided by 2. All you have to know is that once you've enabled your objects to be populated in the column store, that's going to happen as just a background process, similarly to what we do with, say, log writer or database writer. Or there's actually lots of background processes in Oracle database. It is controllable. We always give you lots of knobs. Normally, the default is fine. If you choose that perhaps you want your objects to be all populated right as the database starts up before your applications access the database, then you can increase the number of populate servers that are available, and then it's a dynamic parameter, so you can then reset it if you want back to the default. So we always give you a lot of knobs to twist. You don't really have to do that, but if you want to tailor it to your workload, your environment, then those options are available. So we looked at that. So let's take a look at some examples. So it's always kind of, now we've talked a lot about how database in memory is set up. Let's see it in action. So let's see, now I'm going to flip over my desktop. So you may see a blank screen for a second. And let's make sure that gets there. Excellent, okay. So you should be able to now see my VirtualBox screen. What I've got here is a VirtualBox. My Mac has 16 gigs of memory. This is about a 12 gigabyte VirtualBox, as much data as I could get in or allocate to the VirtualBox. It's running a 19.8 database. I'll show you the parameters I used to set it up. And let's see. So we have an SGA target of basically 10 gigabytes. And then I've set the in-memory size parameter to 5 gigabytes. Also notice I've actually allocated a keep pool. I've only done this so that for the scripts that we're going to run, and especially the queries, specifically the queries, when we compare the speed and what the workload that occurs between the row store and the column store, because I'm going to show you both, the row store data will be fully in memory as well. Very often I get asked the question, well, if I just cache the entire table in the buffer cache, wouldn't that be just as fast as database in memory? It's all in memory. And my point of that is to show you that the columnar format and some of the other technology we have embedded in Oracle database for database in memory gives you or at least one order of magnitude, and many times many more orders of magnitude, faster performance than the row store itself, which is where the value for database memory comes into play. So normally you wouldn't do this, but in this particular case, I've basically split my column store and my buffer cache so that there's almost as much space in both, so that we can actually see a memory to memory or apples to apples comparison. So hopefully that's clear. And then since whoops, the whole point of creating these scripts was so you wouldn't have to watch me type. So if we want to look at the SGA, select star from $SGA, show SGA. Notice that I've already done this, so we wouldn't have to wait and go through the exercise of setting this part up. But there's a new in-memory area in the SGA, and you can see that here, in addition to the $$ in-memory area view. So you can see that we've allocated an in-memory area within the SGA, and that's what we're going to be working with. Typically, we're using the star schema benchmark set of tables, so I'm going to show you that. So we have a line order table, which is our largest table. And then we have dimension tables associated with it. Notice I've set up the cache parameter, set it to Y or yes, and the keep pool, and that's just to basically show you that we've got data in row store fully cached in memory when we compare it to the column store. I'm using disk compression only because it's my virtual box. I don't have lots of memory, but I've enabled each of these objects to be populated in memory. So the enabling and the population are two distinct processes. I'll show you how I enabled them, and then asynchronously in the background, we saw those the picture in that slide. That data will be populated. I have a priority of none, which is the default. This is used. The distribute features are used for rack databases. Talk a little bit about that. And by default, mem compress for query low, so we should expect at least a 2x compression rate. That's the default. When I populated this, and I didn't want to make you guys go through and look at the actual population or wait on the population. It's pretty quick, but in the interest of time, what I did is I ran this script and literally just said alter table in each of my 5 tables enabled for in-memory. And that's it. That's all I had to do. So I've set the in-memory underscore size parameter, recycled the instance, altered these tables to be in-memory, and then I access each of them. Actually, the way I did that, full disclosure. And this is part of our hands-on lab. You can do this now in live labs. We have an in-memory fundamentals lab, which I'll show you the link to. So you can try this out for yourself. Plus on the resources page, I have a script of all of the things that I run and how it works, or you can try it yourself. And so I will show you that a little bit of typing, but not too much. To start population, what I did is I just selected, since I have a priority of none, we won't automatically populate those objects. If I had set a priority of, say, high, then those would have automatically populated. But instead, I just access that data. The only reason these hints are here is so that we get that data also fully cached in the buffer cache. Again, strictly for the demonstration, you normally would never need to do that. This is just so that we can do an apples to apples comparison. Hopefully that's clear. So let's take a look at $IM segments. So you notice that we've got our 5 tables populated. The disk size and then in-memory size. Notice that that's about the same, and that's simply because it's compressed on disk. Depending on whether you use compression on disk or not, you will see the disk size versus the in-memory size. So whatever that is. And then the key column here, bytes not populated. And notice we have all of the bytes populated for each of those tables. So we fully populated those objects in the column store. And then the other view that I showed you in the slide was $$ in-memory area. And notice that we've got roughly 5 gigabytes, 5.5 gigabytes of in-memory size, the parameter allocated in the SGA. Of that, I've got about 5 gigabytes allocated to the 1 meg pool, and less memory, obviously 500 megs or so allocated to the 64K pool. And then you can see how much data was actually used for the population. And so we still actually have some space left over. And that's all just Oracle database. So with that, let's flip back to some slides, tell you a little bit about how it works accessing data, which is really the important part. And then we'll tie up with some of the other aspects and features of database and memory. So let's go back. You may see a blank screen for a minute. There we go. Excellent. Okay, so the database and memory, the underlying technology, we've seen that we can populate these objects. I've told you that we're going to populate them in columnar format. That's the in-memory database and memory part of it. One of the nice things about the columnar format is that for your queries, you only have to access the columns that are part of the query in the column store. Unlike the row store, where we read a database block into the buffer cache and have to traverse each row to get to the column attributes that you've got in your SQL query, we only have to, in the column store, only have to access the actual columns themselves in this columnar format. Now we're going to do a table access in-memory full. We'll talk a little bit about that and I'll show you an example. But we're only going to access the columns we're interested in. In addition, compression. So I said we get about a 2x by default, 2x compression rate. We have something we call in-memory storage indexes. So similar to what we do with Exadata, for each of the IMCUs, remember objects made up of one or more of these IMCUs, for each of the columns, we'll have a min-max value so that it's possible for us to skip scanning an IMCU if, based on your filter predicate, your where clause predicate, or where clause statements, filter predicates, if they're outside the range of the values that are in that particular IMCU, we can skip it. So just an optimization we've added. And then SIMD vector processing, single instruction, multiple data. The ability to do array processing is essentially the ability to actually compare values up to 512 with the AVX512 feature in modern OSs. Be able to do that in essentially one cycle. It's not exactly one cycle since we have to load the vector registers, but Intel and Spark chips have vector registers to take advantage for graphics, and database and memory with Oracle database can take advantage of that to speed up comparison of values and essentially go from scanning millions of rows per second per core in the row store to scanning billions of rows per second per core in the column store. And that's basically what I've said here. I included some slides for some more detail, but the bottom line is we only have to scan the columns we're interested in. We actually do compression. We've got some blog posts about compression that we've done in some Ask Tom sessions, but there are multiple levels of compression. At the query low and high versions, we do symbol replacement. At the capacity low and high versions, we add zip-like compression on top of that. Typically, DBAs will freak out and say, oh, we can't do that because it'll take up so much overhead. The reality is the space benefit versus the cost to the query, because remember, we're still in memory, so it's still way faster than the row store. For many customers that have memory constraints can far outweigh the negative benefits of the higher levels of compression. Again, your mileage will vary. You should try it out. That's kind of the best way is on your data. Don't dismiss the capacity versions for giving you a larger memory footprint, because they can that can very often far outweigh the slight cost in CPU to decompress at the high levels. Kind of my pitch there. Again, there are more details on our blog. I mentioned the in-memory storage indexes and the SIMD vector processing. So the other aspect to database and memory is the optimizer. So I mentioned, kind of the secret sauce and the ability to not have to change your SQL to take advantage of database and memory is the ability for the optimizer to choose, do I access that data in the row store or the column store? I mean, you don't say select data from the row store or select data from the column store. You just say select data from the tables you need to access that data in. And the optimizer, based on cost, decides what objects it will access either from the row store, maybe through an index, or the column store, table access in memory full. So I'm going to go in a little more detail in this aspect, because I think it's very interesting. We just did an Ask Tom office hours session on pushdowns, but the bottom line is not only can we just access the columns involved in the query in the column store, we can actually also push filter predicates and function-based aggregations and evaluate those during the scan of the data, as opposed to having to bring those row or column values back into the upper layers of the execution plan and then throw away the non-matching rows, or do the aggregation, say for a min or a max during that part of the execution. So this gives you a significant speed up, and that's why we do it. So the ability to push down filter predicate evaluation and aggregations into the scan. In addition to that, joins. So we can turn hash joins where we normally would have to create a probe table in the PGA and probe those values in the probe table and the smaller table, in this case the stores table, and to see if we have a match in the join condition. We can actually create a Bloom filter and push that join condition into the scan along with any other filter predicates or aggregations, and essentially change a hash join into a scan and filter operation. can get a significant performance improvement with that. And that's an optimizer decision that's made at parse time. In addition to that, group by aggregation. So typically, also in Oracle database, we've had sort group bys. In 11, I think it was early 11, we added a hash group by. Well, with database in memory in 12.102 and above, we've added something called a vector group by, or in-memory aggregation. And so what this allows us to do is actually not only do we can do the join in memory, so essentially a scan and filter operation, but we can also do the aggregations, the group by aggregations in memory as well as part of the scan. So not only can we change a hash join into a scan and filter operation, we can change a group by aggregation to a scan and filter operation. Now that's a very high level view of that. We don't have time to go into the details of it, but there is an in-memory, well, it's an in-memory, but it's in-memory aggregation technical brief that goes through and talks in detail about how this works. It's very interesting. We use key vectors rather than Bloom filters because we're going to create a in-memory report aggregate accumulator, and we'll do the group by aggregation as we do the joins and scan of the largest table. There's actually quite a few details associated with that, but it's fascinating technology. And another part that you only see a vector group by if you've got in-memory enabled. And so that's another advantage that the optimizer can take another feature the optimizer can take advantage of to speed up your analytic queries. So think star queries, OLAP, maybe being able to eliminate, and that's actually what one of the key parts of this was, eliminate your cubes, your pre-computed cube type structures. You can just actually run your in-memory queries using vector group by right on your existing data, and without having to pre-compute cubes or bitmapped indexes, perhaps. A lot of features that you had to do to get analytic and OLAP type queries to run in the row store can run with database and memory without having to do anything. A very powerful feature. All right, so let's look at some of the queries to back up what I've just talked about. We're going to flip back again. Apologize, but this is how this works, and it's actually not too, I haven't screwed it up, so it isn't too onerous to do this. So you can, yes, okay. So let's take a look at some of our queries. So the first thing we'll do is just look at a straight in-memory query. Whoops, this one right here. We're going to literally just select the max total order price, one column from the line order table, no where clause, nothing particularly fancy, just an aggregation. Remember I said we could push function-based aggregations into the scan. So we'll take a look at that in a second. Ran very fast, 0.04, 0.04 of a second. Notice table access in-memory full, so the optimizer decided that it made sense to access the line order table from a column store. We have roughly 60 million rows, 59 million rows. And it wouldn't be Oracle database. We have session statistics. Very often, the session statistics are an excellent way of, if you're experimenting, of determining how much value database and memory provided. I also talk about SQL Monitor active reports, where time was spent, but in this case, we're kind of experimenting. So I'll tell you what some of these statistics mean. We do have I have a blog post that describes some of the more popular statistics. In addition to that, some of them are also documented in the Oracle reference manual. Not all of them, so hence the blog post. But what we see here is mem compressed for query low, IM scan CUs. So what this tells us is that we have 111 IM CUs that make up our line order table in the column store. And the IM scan rows projected tells us that we brought back, and it kind of makes sense if you think about it, we scanned each of the IMCUs and we determined the max value based on IMCU, and then those 111 values were then aggregated together to give us our answer, as opposed to having to look through and aggregate all 60 million rows in the upper part of the execution plan. So we were actually able to do our aggregation during the scan of our line order table. So let's compare that to the row store. So what I have is the same query, basically. Notice I put a no in-memory hint. Again, it wouldn't be Oracle database if we didn't have hints. We have statistics, the optimizer, the execution plan, table access in-memory full. But bottom line is that what this says is tells the optimizer, don't consider the column store for this query. Use the row store. Otherwise, the same exact query. Notice it took 11.5 seconds to run. This is on my laptop, so your mileage obviously will vary, but significantly slower. 0.04 of a second. We did a table access full because we don't have a where clause predicate. We're just adding up for the total line order table, all of the rows, for the column value for the total order price. And then notice that there are no physical reads. So just session logical reads. We accessed all of those rows in the buffer cache, essentially a logical read instead of a physical read. I will show you the query that I'm using to take a look at the statistics and notice that I'm looking for physical reads, but we're not doing any. So it's literally a memory to memory comparison, and it ran in 11.5 seconds in the row version of it, and it ran in 0.04 of a second in the columnar version. So that's kind of that, would it be just as fast to cache the entire table in the row store? And the answer is clearly not. So let's look at some of the other features of database in memory. So we talked about, talked a little bit about indexes and the fact that you might not want to drop all of your indexes, but you typically get rid of most of your analytic reporting indexes. But what about OLTP? Well, can I still use database in memory on a what I would call a mixed workload environment, or one where I'm running OLTP and reports? Will it interfere? And so let's take a look at, I've got whoops, sorry about that, an index comparison. So what we're going to do is we're going to run a query with a where clause predicate. We're only looking for essentially one row. Notice that I told the optimizer to use invisible indexes. So I've pre-created some indexes and made them invisible so the optimizer wouldn't be able to use them. But in this case, I said, well, go ahead and use the index if it's available and the cost makes sense. And it said, okay, I have a line order I1 index I accessed. That made sense. Notice it says we accessed that LO order key. So we're going to filter on that particular item. We got one row back, ran very, very fast, and great. So we didn't access in memory. That makes sense. OLTP could use indexes, even though the tables populate in the column store. Based on cost, it makes sense to access that data through the row store. Well, okay, so that's not the entire picture. So for comparison purposes, let's take a look at what happens to the same query, but now the indexes are invisible again. So the optimizer can't make use of it. We get our one row back again, runs close to the same speed, maybe not quite as fast, but pretty darn close. Remember, we're looking through all of the column values for that object. Take a look at that in a second. Table access in memory full. Notice that now we actually have something that says in memory LO order key. What this tells us is the optimizer is going to push that filter predicate into the scan of the line order table. And if we look at our statistics, remember that I said we had 111 IMCUs associated with the line order table being populated. Notice the second column or statistics that has shown up. It says IMCUs pruned 110. What does that mean? Well, if you think about it, remember the in-memory storage indexes? Since we're only looking for one row, we're only going to get one row back. So we're only looking for one row in essence, or one set of column values associated with what would be a row. We're only going to have that data in one IMCU. So what has effectively happened is using in-memory storage indexes, we've been able to prune or skip over 110 10 of the IMCUs and just access one IMCU. So effectively, the scan is almost as fast as if we had an index. Now notice here the cost is a little higher than the row access that cost from an index, which is why the optimizer would choose an index scan. But in more complicated queries, more complex queries, it very often can occur that can help give significant speed up to database and memory queries by being able to skip over or not do work that's not necessary. Before we run out of time, let me show you a couple more what I think are interesting features. We talked about hash joins. So let's look at a hash join. So we've got a little more complex query, just the line order table and the date dimension table. We have some filter predicates, and it runs very fast. We're going to aggregate our sum. So remember, we're thinking, so we can push that sum and those filter predicates into the scan of the line order table. But we also have to scan the date dimension table. So what does that look like? Notice that now we're going to scan the date dimension table first, but we're going to create a bloom filter. Remember I said we can change the join column or the join itself into a scan and filter operation by using a bloom filter and pushing that bloom filter along with our other filter predicates into the scan of the line order table. And notice the optimizer's actually done some optimizations with our filter predicates as well, because here we had our filter predicate as between 2 and 3 for the discount, and the optimizer has done a little rewriting and created a bloom filter, and we're now pushing that bloom filter. So we're doing the join during the scan of the line order table. We scan the date dimension table, so that's scan number 1, create the bloom filter based on filter predicates for the date dimension table. We had one with the date, and then using that bloom filter plus the other filter predicates on the line order table, we're scanning the line order table and then returning the result. So we don't have to do any other work. We do have to actually check the probe table to materialize any columns in the select clause, but we don't actually have to rescan the date dimension table to do that, and it makes it much faster than a traditional hash join not using this technology. And you can see that in some of the statistics. Again, notice that our scan rows projected, so we only have to bring back 2132 rows or column values as opposed to a much larger amount in the row store. In the interest of time, though, I want to show you the vector group by, and then we'll tie up with some of the other technology that's available in database and memory. And again, all of these examples are available on the resources page if you want to go take a look in more detail about how that works. And actually, I should mention, also there on our hands-on lab book and in the live labs, if you choose to go through that to do that, I've got very detailed explanations for you of what's going on. So this is, since we only had an hour to do this, we have a lot to cover. I'm not going into as much detail, but you can get that detail in some of the other collateral I've got available to you. So now we have a little more complicated query. We're going to actually look at, we're going to take the year and nation and sum the total, essentially, profit using a join against all of our both our fact table and our dimension table, so all 5 of our tables. We've got some join criteria, some filter criteria, and our group by of year and nation to do our aggregation. So we're doing a group by aggregation. So we get that data back, runs pretty quick, 2.3 seconds. The interesting part of this is notice that our execution plan has changed significantly. Now we're creating key vectors on each of our dimension tables, and we're then applying those key vectors to the scan of our line order table. Again, remember there's an in-memory aggregation technical brief that talks about all of the detail here. The takeaway really that I want you to get is that you can now with database and memory use a vector group by, something that you probably haven't seen before, sort group by, hash group by, but now a vector group by, to significantly improve group by aggregation performance with database and memory right on the source data, that real-time analytics part of the equation. So with that, let me switch back. We may run a little short on time, but I only have a couple slides that I wanted to finish up with. There we go. Good. How do you know which queries will benefit from database and memory? So we've kind of gone over scanning data. If you're spending a significant amount of time scanning data, joining data, or aggregating data. How do you figure that out? SQL Monitor Active Reports. If you are not familiar, we have a technical brief on the blog on the resources page. Bottom line is, using SQL Monitor Active Reports, it's possible to determine how much time is spent in memory. Notice I've got an arrow highlighting that. SQL Monitor will tell you the difference between normal CPU time and in-memory time spent, CPU time spent on in-memory processing in the column store. Very valuable. We have quite a bit of documentation that talks about how to evaluate that in our quick start guide, in our implementation guide. So I would suggest, if you're interested, go back and take a look at those. And then in addition to that, you might ask, well, how much memory do I need? The in-memory advisor, which we have available on oracle.com, can download that 11203 or greater database. It accesses AWR and ASH data. It can provide you with a pretty good guesstimate on not only does your database workload have analytic reporting and how much benefit you might get with database and memory, but also how much space you might need and what objects you might want to populate. In addition to that, there's a compression advisor. It's been enhanced to also take into account the compression of the in-memory column store, so you can run the compression advisor against individual objects to see how much space will be required for those objects. Does it work with other database features? Of course, the answer is yes. Exadata, I mentioned the ability to use not only DRAM or the in-memory column store, but also the flash cache on Exadata can be used for the in-memory columnar formats. So if you don't have a memory to fit everything in the column store, it will also, if it's smart scanned and not populated in the column store, will be brought into the flash cache, reformatted into database and memory columnar format, and can be accessed there. So essentially that gives you essentially 2 tiers of columnar storage, which then can be terabytes in size. So very powerful feature. It's first added in 12.2 and has been continually enhanced. And actually that's what ADW uses. So on ADW, the Autonomous Data Warehouse, we're using the flash version of database and memory to help speed up those data warehousing queries. So we fully support rack for scale out. As much memory as you can put in your database server, if Oracle database can address that memory, database and memory can make use of it. Fully supports multi-tenant as we move into the next releases of Oracle database. All we'll have available to us is the multi-tenant framework. Database and memory fully supports that. And no matter where your data is located, whether it's DRAM, flash, on disk, doesn't matter. Database and memory, if you've populated data in the column store based on cost, we'll access it there if it makes sense, or wherever else your data is. Again, we haven't changed the Oracle technical architecture of the database, so everything still works the way it did before. Rack, ASM, Golden Gate. Actually, the 2 key takeaways here are DataGuard, Golden Gate, your backup technologies. None of that changes with database and memory. And one of the most exciting things I wanted to mention, this kind of slide, it basically tells you all of the things we've been adding to database and memory. The most, I think, exciting new feature is going to be automatic in memory, where we'll actually automatically populate the column store based on usage. And I want to close, so I'm going to run out of time, with something we added in the 20.3 pre-release feature and backported to 19.8. I mentioned it at the beginning. It's called the base level feature. The ability to populate or allocate up to 16 gigabytes of the column store without having to enable the database and memory option. You set the do I have that documented? I think I do. The in-memory force parameter to base level, so 19.8, 20.3 pre-release, but in the future, on the next version of the Oracle database, excuse me, if you can then set the in-memory underscore size parameter up to 16 gigabytes and take advantage of database and memory without having to pay for the database and memory option. The point of this is now you can, on your existing workload, can see the value of database and memory. All the other features effectively work with database and memory. There's a couple limitations. I'll point you to 2 blog posts we've done that talk about that in an Ask Tom office hours session. And with that, I'm going to close and thank you for attending the session. I don't see any questions, which is good since I kind of ran over a little bit over time. We did get through everything. Hopefully that gives you a good feel for how database and memory works. If you have questions, my email address is at the beginning of the slide deck, and this URL will get you to kind of all things database and memory. And thank you very much for allowing me to speak with you this morning. And if you do have any questions, I'll be more than happy to answer them until they kick me off. It looks like Brent might have a question, but I don't see maybe you're still typing. Does it always load the whole table into memory, or can I? So yes, you can. If you have partitions, you can populate just the partitions you choose. You can even exclude columns. You don't even have to populate all of the columns in the column store. You can actually exclude columns as well. So hopefully that answers that question. If I don't have anything else, we'll see if I get kicked off here. Okay, good, you're welcome. But please, there's multitude of ways of experimenting with database memory. If you're interested, feel free to take advantage of it. The live labs is probably the easiest way. I have the link in the resources page, or you can search on database and memory live labs. So with that, I guess we'll call it a session, and thank you very much for attending.